We've been talking in Chapter 12 about statistics and probability. And today, we're going to talk about a couple of topics that I'm going to call outcomes and theoretical probability. We're going to deal here with scenarios where there are multiple possible outcomes, and we're going to talk about what possibilities there are. Outcomes, by the way, just mean the number of possible ways that a scenario could or can turn out. So if you're rolling a die, how many outcomes are there? Well, there's 6, right? You could roll a 1, you could roll a 2, etc., etc. If you're flipping a coin, you've got 2 different outcomes, heads or tails. And if you're pulling one random card from a deck of cards, you've got 52 different outcomes. This is not difficult. What you also need to know is the phrase sample space. Sample space is the list of possible outcomes that might happen. It's making a list of those number of outcomes. So we would make a list of ace of clubs, 2 of clubs, 3 of clubs, ace of diamonds, 2 of clubs, 3 of blah, 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 blah. This list would be really long, and you can see a picture of it right here. Now, the sample space for flipping coins would be pretty easy. Heads, tails. Your list only has 2 different outcomes on it. And if you're rolling a die, you've got a sample space of a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Not too difficult to understand the idea of sample space. It's just a list of what could happen. Now, speaking of what could happen, this morning, as I was getting dressed, lots of things could happen. I had all these different sweater vests to choose from, and I had 4 clean shirts to choose from. How many different outfits could I make here? If I've got 4 shirts and 6 sweater vests, how large would my sample space be of possible sweater vest shirt combos? In other words, if I made a list of black sweater vest, blue shirt, black sweater vest, white shirt, black sweater vest, gray shirt, black sweater vest, other form of gray shirt, yellow sweater vest, white shirt, etc., 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 it'd be pretty boring to make that list. But if all I wanted to know was how large the sample space would be, just a number of possible outfits, I don't need to actually write out the sample space. I could figure out the number, the size, by just doing this. Take your 6 sweater vests, take your 4 shirts, and multiply those 2 numbers together. And that will give you 24 possible outfits. And I know that there are 24 without having to list them all out. Okay, that's pretty convenient. Now, it's probably important for me to wear some pants today too. So, how many different outfits could I make when I put pants into the equation? Well, it's still 6 sweater vests and 4 shirts, and I'm still going to multiply those together, but now I'm going to multiply by 2 for the 2 pairs of jeans. There are actually 48 different outfits that I could make using these items of clothing. This is something called the counting principle, or the fundamental counting principle, or sometimes called the basic counting principle. And what it says is if you want to know the number of outcomes, just multiply all the numbers together. You might have already known that. But if you didn't, now you do know it. And this is actually a really powerful tool in math. You can find out the number of outcomes just using multiplication. All right. What about shoes? What if I have my black Chucks, or my gray Chucks, or my kind of slightly greenish Chucks? Now, I'm going to have 144 possible outfits because it's 6 times 4 times 2 times 3. And you can check the math yourself on that if you would like to. What if I wanted to know how many different possible phone numbers there are in the United States of America, where we generally have a 3-digit area code followed by 3 more digits and then a dash and then 4 digits after that? Well, let's go digit by digit. The first number of your area code could be any of 10 different digits because it could be 1, 2, 3, 4, 5, 6, 7, 8, or 9, or it could be a 0. I don't know if any area codes actually start with 0, but it could be. How many different numbers could the second digit be? There could be 10 different digits that can go there too. And 10 different digits that could go there, and 10 different digits that could go there, and 10, and 10, and 10 more, and 10 more, and then, oh my gosh, how many different phone numbers would this be? Well, if you multiply that out, it's going to be 10 to the 10th power. So how many different possible phone numbers are there in this schematic scenario? There are about exactly 10 billion possible phone numbers in the United States of America. Okay, Now you get to try this. I'll make it slightly easier for you. How many different 5-digit zip codes are there possible? I bet you could figure that out, right? All right, now that you've figured that out, let's talk about Monopoly. You've all played Monopoly, right? Let's say you're playing Monopoly, and you're on, I think it's New York Avenue. And no, let's say it's the one right before that. And you really want to get to the free parking so you get some cash, but you're 2 spots away. You've got to roll a snake eyes. How likely is it for you to roll snake eyes? What's the probability of you getting 1-1 on your 2 dice? Well, here's the sample space. When you roll 2 dice, you could get 1-1, 1-2, 1-3, 1-4, or you could get 3-3, you could get 4-4, you could get 4-6, you could get 4-1, you could get 6-3. There's a whole bunch of different things. Actually, there's 36 different outcomes that are possible when you roll 2 dice, number cubes. What are the chances of those 2 numbers both being a 1? Well, only 1 out of those 36 items in the sample space are snake eyes. So you have a 1 in 36 chance of getting double 1s. Now, if you don't want to bust out a sample space diagram every time you play Monopoly, you can actually figure out that you have a 1 in 36 chance using the counting principle. Let's take the first die. Don't you have a 1 in 6 chance of getting a 1? And don't you have a 1 in 6 chance of getting a 1 on the second die? Well, if you multiply those together, you get 1 times 1 on the top and you get 6 times 6 on the bottom. So that tells you that you have a 1 in 36 chance. Basically what I'm trying to tell you is the counting principle works for probability fractions, just like it works for finding the number of outcomes. All right, so what's the probability of flipping heads 3 times in a row? Well, on your first coin, you have a 1 in 2 chance. On your second coin, you have a 1 in 2 chance. On your third coin, you have a 1 in 2 chance. So on top, you have 1 times 1 times 1. On bottoms, you have 2 times 2 times 2. So you have a 1 in 8 chance of that particular occurrence taking place. All this is multiplication. It's really easy. All right, so here's the last challenge. If I were to pick out an outfit completely at random, I turned the lights off in my closet and just reached randomly at things, what are the chances that my sweater vest would have blue on it, my shirt would be gray, and my jeans would be faded? What are the chances? Like, give me a fraction for probability. Or, hey, you could give it in a percent or a decimal too if you wanted to. But what would my probability be? All right. Once you figure that stuff out, you got the basic idea. Hope you enjoyed this video, and I'll talk to you later.